Evening, everyone. Welcome back to Integrated Life Session. So today we will be talking about the lectures that have been covered in week 2, and followed by that we will be taking some problems. We will wait for a few other people to join. And if there is any doubt or question from the last session, please let me know before we jump to the next topics. So we will shortly start with the topic that we last actually discussed about the catalytic cyclopropionation. We just gave a reaction and we discussed a few things about it. So we will be talking about this catalytic cyclopropionation in full details. Followed by that, there are some other, we will be talking about the coupling reactions that we are going to see that how CC bond formation happens. And followed by that, the mechanism, the examples, everything we will be discussing full details. So in going from that flow, if you feel any doubt or question, you can just unmute yourself and ask the question, or you can put your question in the chat box. And followed by that, we'll be taking up some problem sessions. We'll wait for a few more minutes for others to join. So you can start. So last time we saw that we were talking about the cyclopropionation. So how it really happens? Because we introduced the carbons, different types of carbons we introduced with the fission shock, followed by the Grubbs reaction that we Grubbs catalyst that we look into different reactions. So here is one more example for which we can consider as the application of those carbons, which is cyclopropionation. So if I have an olefin, or you can call it as an alkene, and in presence of the carbene equivalent, and the catalyst, so we expect it to form one more, because the carbon will give you the CH2 group. So one extra carbon will come and therefore it will form a cyclopropane group where the substance will remain as such. So at these carbons where we were having an alkene bond, now we are having a cyclopropane group. So in this scenario, the commonly used catalysts are first one, we know that palladium we can use if we are having a CH2N2, which is diazomethane. So this works as a carbon equivalent, or rhodium with combination of copper iodide. This can be used for diazoester. So sorry for the voice. Come back here. What I really mean to say by carbene equivalent is like when you have a metal center, when you have a metal center, which I am considering as M. And now when I'm taking a carbene, which is diazomethane, okay. So this can be rewritten as CH2 minus and N2 plus, right? Now when we have M in vicinity of this particular charge species, they will interact making M minus CH2 and N2 positive. Now once this charge comes into picture, this N2 which is having a positive charge that releases and forms N double bond CH2. Now this is your metal carbon. And this is your metal carbon equivalent, right? So this becomes an active intermediate for getting that reaction to be done. So I hope this is clear that we are taking an olefin and we are making a cyclopropane out of that using a carbon equivalent. And different catalyst is being used when we are using a diazomethane as a carbon or diazoester, their rhodium or the copper iodide. Now, there can be a question that additionally added carbene that we are using is the intermediate or the intermediate which is forming from the M double bond CH2 that is carrying out the reaction. So how do we prove that the methyl carbene intermediate, which is your M double bond CH2, is actually generating from your diazomethane and is responsible for the reaction, which is catalytic cyclopropionation. So how do we prove that? So for this, solution would be, let us first take an example of where we have R2N. This is a chiral center I'm marking here, and followed by an olefin and a fire. Right? So now this is a chiral substrate. Followed by that, when it is being reacted with CH2N2, which is diazomethane, in presence of palladium acetate catalytic amount, what we expected to form should form Instead of that olefin, now there would be a cyclopropane group, and so this can be having certain stereochemistry. So the two stereomers will form as 93:7, and this particular is 86% diastereomer. Now, the question is the evidence where the metal carbene is intermediate in cyclopropanation reaction. So that we have to now look into picture. So we have first example of a homogeneous transition metal. Okay, so we were talking about a first example of homogeneous transition metal catalyzed in entroselective cyclopropanation. So if I'm taking a phenyl olefin with a diazo ester. Now this would make a new carbene with a metal center and a copper catalyst. That's why I mentioned a transition metal base system. Now what we expect at this particular olefin, we will be having a cyclopropane group formed. This whole group CO2 ET will come over here. So to prove that this is the copper carbene, which is actually giving the enantiomer selectivity over here, we need to have a chiral copper catalyst. And for that, we should have chiral ligands involved in this one. So this will give you direct evidence that actually this carbene, which is coming from the metal interaction, is the actual intermediate which is carrying out the catalytic cyclopropionation and not the free carbene which is present over there. So in that case, if you have a chiral system, if it induces the chirality in your system, like in this case, then we can say that it is coming from your that metal carbene is involved. For example, in this case, the free carbene. So there are two potential carbenes in this particular case. Two potential carbenes which are in competition with each other. In this case, one is, if you see, we have a diazo ester, and this will turn into, here it would form a CH2 carbene and double bond OET. So this is basically your free carbene. Followed by that, we will be having the carbene which is formed with the metal center, like this way. This would call as a copper carbene. And if this copper center is having a chiral ligand, L star, then it would give you a asymmetric synthesis of this cyclopropane and would lead to the conclusion that metal carbon is the one which is the intermediate of this one. Let's look at the industrial application of such systems. This leads to the formation of a celastin, which act as an antibiotic. If you take this carbene, the substrate, the olefin, and then a source of carbene, which is diazoester, in presence of a chiral copper catalyst. This is chiral. It would give you a cyclopropane group here, methyl, and a stereo center at this position. This can further form the used in the formation of a cilastatin, the antibiotic. I hope this is a bit clear. So this was all about our catalytic cyclopropionation reaction. Now we are moving to another topic, which is various CC bond formation reactions. So these are generally on a larger scale palladium catalyzed carbon-carbon coupling reaction. So where we are going to see first this synthesis of sp2 carbon bond, meaning that if I want to form a bond between two phenyl groups, this is sp2 carbon, this is sp2. So this bond formation is very difficult, but this is feasible by doing the coupling reaction. So how do we do the coupling reaction? Generally, we have Rx, which can be your aryl or alkynyl halide, and then you have R-M. This is your coupling partner, followed by you have palladium catalyst, and it will give you a product R dash. So there are different names. There are different names with different coupling partner. So the reaction was X plus R dash M. It was giving R dash, right? So if your M is lithium or magnesium, The reaction is named as Kumada coupling reaction. If it is boron-based partner, then it is Suzuki reaction. If it is tin-based, it is Stille reaction. If it is zinc, it is called as Negishi reaction. And if it is silicon, it is called as Hiyama reaction. And these are very, very important named cross-coupling reactions. So with respect to the name, you need to know, or vice versa, like which coupling partner is involved in the reaction. You cannot get confused with these systems. Now we'll look into the general mechanism that is involved in the coupling reaction. So general CC cross coupling reaction mechanistic cycle. So it has to start with, even if you are taking a palladium plus 2, it has to start with active palladium 2, palladium 0. So this is active palladium 0, followed by it would form, it would react with your substrate, which is your aryl or alkyl halide, and the step is called as oxidative addition OA, where the palladium is going to change its oxidation state from 0 to palladium 2, because the 2R and X will get coordinated with this one. Once its oxidation states gets changed and substrate is involved, now you have your coupling partner, which is R dash M. When it gets involved in this one, it releases, it takes out the halide, and R dash replaces the halide, forming palladium 2, R, and R dash, Ln. This step is called as transmetallation. Now, the third and last step would be your reductive elimination step, which would form RR dash. This is the third step, which is reductive elimination, and would lead to Ln palladium 0. So here we have first step, which is called oxidative addition. Where palladium 0 goes to palladium plus 2 state, and substrate aryl or alkyl halide gets coordinated with palladium. The second step is transmetallation, where if we have Rx and it is having Rm dash, it will form Rr dash and it is Mx. So here transmetallation is happening. And the third step is your reductive elimination, which would release the product and make palladium 2 to palladium 0, which is again the active catalyst, and the cycle continues. So these are the three specific steps that are involved here. Out of all these steps, we first talk about the transmetallation step. This often this often works via sigma bond, metathesis. Metathesis also we saw in our first week lecture. Here if we have palladium X and R dash M, this is transmetallation, it has to be between two metals. So when you are doing this way, it is sigma bond metathesis, where this will undergo the bond breaking happens here and bond formation happens here. So we will make the bonds with different colors, and this is your transition state. Bond breaking I'm making with the red bond, and the new bonds are being formed as yellow color. So the yellow color is bond making, and the red one is defining bond breaking. So this is what we call in bond method sigma metathesis, where it will then end up making the palladium R dash bond and MX bond. Now let's start with our first named reaction, coupling reaction, which is Kumada coupling reaction. This was given in 1972. So here basically we are having the general reaction, a halide source. Here it can be lithium or it can be magnesium, which is your organolithium or Grignard reagents, basically call them. Highly nucleophile. So in presence of a palladium catalyst, it would give R dash. So here common catalysts that have been used are palladium PbH4, cyclopentadienyl ring. This is ferrocene, which is having a substitution of PbH2, PbH2, and this forms bond with palladium. And the other one, phosphate is a neutral ligand, as it is only giving the lone pair here. So palladium is getting charged from chloride only. So these are the general common catalysts that we use. So here, as we said, that the active, as I mentioned, catalyst is palladium 0 and not palladium 2. But when we are starting from palladium 2, how it generates the palladium 0? So generation of active palladium 0 from palladium 2. So the organolithium that we are using, it basically helps in getting it reduced. So when we are having a palladium Cl2 where this is your ligand and we are using little axis of your organolithium, and this helps in taking two lithium fluoride outside, forming R and R. This on forms palladium 0 plus R dash and R dash. This is your side product, and this one is your active species. One example that we are going to take, we have alkyl bromide source and butyl MgCl, which is Grignard reagent in presence of catalytic amount of palladium DPPF Cl2, we end up getting double bond and butyl group, which is formed 90% yield. The important point here is retaining the trans conformation. So it retains a geometry in case of the Kumada reactions. Now there is another feature, the selectivity E versus Z isomers in Kumada coupling reaction. Now if we have this substrate, so when we are taking a mixture of these two as 67 is to 33, which is 2 is to 1, mixture of substrates, and when we call it as A and B. So when this A and B are there as 2 is to 1, in presence of the catalyst and 0.06666 equivalents of anthropyl magnesium chloride, which means it is also 2 equivalents with respect to A, and therefore only trans product we got as the exclusive product. So the take home message is even if we have a mixture of isomers, cis and trans, the major isomer will lead to the product
formation, as in this case, this isomer will not even react. This is what we have learned about the Kumara reaction.